All right, so let's get started. Again, last class we introduced this chapter 19, which revolves around thermodynamics. Work. Okay? All right, so just to crash course review what we learned last class. We said that scientists set out to find this chemical potential, this measure of whether or not a reaction will occur. All right? They knew it was going to have to involve enthalpy, this study of heat, because they know that most reactions like to release heat. All right, but that couldn't be the whole story. So then they hit upon this concept of entropy. And entropy has a pretty wonky formal definition, but again, the best way to think about it, is that it's this energy of disorder. Right? The universe likes things to be in a disordered state. Okay? So much so that they came up with this second law of thermodynamics, which says that nothing happens in this world unless it increases the entropy of the universe. So every chemical process that happens, any process that happens only because it increases the entropy of the universe. Okay? But then they had this okay, well, wait a minute. There are certain processes that we know that are entropically unfavorable, right? Such as the freezing of water into ice, but it still happens. So why does the universe give that a pass? And so for that, we sort of have to remember, okay, well, we can break the universe up into two parts. The actual system, okay, and this is our reaction. But then there's everything else around that reaction as well, right? So we're going to cut the universe up into two parts. The thing that we're looking at, the reaction, and then everything else, the surroundings. Okay? So then how can a chemical process occur if the delta S of the system is less than 0, right? Meaning that this is an entropically unfavorable process. That's okay if the delta S of the surroundings is greater than 0. Okay, and then delta S of our surroundings, that's just the negative enthalpy of the system divided by temperature. All right, so the bottom line here is if we're going to try to answer the question, why do entropically unfavorable processes still occur? All right, because they have a negative delta H value. If it's negative delta H, what does that mean? It's exothermic or endothermic? Exothermic, right? Why? Because they're exothermic. Which means they release heat into the surroundings. Increasing the entropy of the surroundings. All right, so if we want to do anything that creates order, anything that's entropically unfavorable, the universe will only let it happen if it's an exothermic process, because if it's exothermic, that means that heat's being released. And so although we're creating order in that system, we're creating disorder in the surroundings, right? So there's still a net gain of disorder. The universe is like, all right, I'll give this a pass as long as on bulk, in total, system plus surroundings, there's disorder being created, right? So if we're going to create order in our system, if we're going to freeze our ice, the only way that's allowed to happen is if that process releases heat and thus creates disorder in the surroundings. All right, so at the end, we rolled this all together into this formula here, where we replaced this chemical potential with delta G. That is our chemical potential, named after the dude who found it, Josiah Gibbs. Okay, so our chemical potential is what's called the Gibbs free energy. Delta G. All right, so scientists for a long time are trying to build this chemical potential. This is this formula that they landed on here, where your chemical potential, what we call the Gibbs free energy, is equal to the enthalpy minus T times the entropy. All right, and T is the temperature in Kelvin. All right, and again, this delta G is going to be a measure of whether or not reactions happen, what we call reactions happening spontaneously, okay? So a reaction is spontaneous if and only if delta G is negative, less than 0. All right, so for a reaction, we can calculate this Gibbs free energy. If it's negative, we know that the reaction happens spontaneously. Delta G greater than 0, we would call this non-spontaneous. All right, but I feel like it's a little bit of a misnomer because non-spontaneous makes it sound like it's not going to happen at all. All right, where actually non-spontaneous really means that it's spontaneous in the reverse direction. Right? Remember when we were talking about equilibrium, we had that, we sort of started our chemistry life cycle thinking about chemical reactions as all reactant being completely converted to product, right? And then in the equilibrium chapter, we were like, okay, well, that's not really true. Reactions can go in either direction. We can set up our conditions such that we actually get the reverse reaction. And so that's what our Gibbs free energy is going to tell us, whether or not the reaction goes forward towards the products or whether or not it actually goes in the reverse direction and favors the reactants. Okay? So again, if delta G is negative, it's a spontaneous reaction, goes towards products. We can even just make a note, that means towards products. If delta G is positive, that was what we call non-spontaneous, but really it just means it's going the other direction, so towards reactants. All right, and then what about if delta G is exactly 0? What do we think that means? Not no reaction, but no movement, right? So that means that your reaction is stuck at equilibrium, right? So it's already sort of made its move one way or the other. It is currently at equilibrium. So delta G equals 0 means that we are at equilibrium. It's not going to favor the reactants or the products. It's good where it is. All right, so what we're going to do with this table here is we're going to use this equation to figure out, like, so using this equation here, let me actually copy this to a new page. Okay, and what we're going to do here is say if the sign of delta H is, for example, negative, right? A negative delta H is what we call what? Exothermic or endothermic? Exothermic. So if our reaction is exothermic, and our reaction has a positive delta S, is that favorable or unfavorable? Right? Entropy greater than 0, that's what the universe wants, right? That would be a favorable, an entropically favorable process. So if we have something that's both exothermic and entropically favorable, what would be the sign of the delta G in this equation? All right, so if we plug in a negative value for delta H, delta S is positive, but we're multiplying it by negative delta T, right? So if I take a positive number and I multiply it by a negative number, this is also going to be negative. So that's a guaranteed way for delta G to be negative, which is a spontaneous reaction. Right? From the universe's standpoint, this is best case scenario. Not only is this reaction releasing heat, so it's causing disorder in the surroundings, but the reaction itself is creating disorder. So this is favorable from like both aspects as far as the universe is concerned. Max chaos going on here. Okay? An example would be like a combustion reaction. Those are reactions that are both very exothermic as well as very entropically favorable because they create a lot of gas molecules. Okay? And what we've learned about those combustion reactions, if you remember from Dr. Yang's video, she was basically saying one of the reasons we're having such a hard time getting away from using combustion reactions as a source of energy is there's like nothing better out there, right? In terms of like the amount of energy that you get per gram of these hydrocarbons from a combustion reaction. There's basically nothing better out there as an energy source because it's favorable not only from an entropy standpoint, but also from an enthalpy standpoint. It's both entropically favorable and exothermic. Let's go the exact opposite. Let's think about the sign of delta G if we had an endothermic reaction, a positive delta H, and a reaction that was entropically unfavorable. So it had a negative delta S. What's going to be the sign of delta G in that case? Positive, right? If this number is positive here, and I got negative T times a negative number. Negative times a negative is also a positive, right? So this is a guaranteed positive delta G. This reaction would be non-spontaneous. Nothing is going to occur in this universe if it is both endothermic and entropically unfavorable. Universe isn't going to let it happen. All right. But what if a reaction is exothermic? So I have a negative delta H. All right, that's good from the universe's standpoint. It likes those exothermic reactions. but it's entropically unfavorable. Okay? Now we got a little bit of a conflict here between these two terms in our equation. Our delta H is going to be negative, but my negative T delta S, a negative number times a negative number, now all of a sudden this term is positive. Okay? So which one of these two terms is going to dominate the sign of delta G is going to all depend on the value of the temperature. Okay? So let's think at very low temperatures. Let's go to the extreme low temperature, a temperature of 0 degrees Kelvin. If we plug in 0 into this equation, would delta G be negative or positive? Negative, right? It's going to cancel out that delta S term altogether. So at low temperatures, this reaction will have a negative delta S or be spontaneous. But as temperature is increasing, there's going to be some point that we cross where now this term, the T delta S term, is going to dominate, and this will be non-spontaneous at high temperatures. All right, so these exothermic processes that are entropically unfavorable, they can happen at low temperatures, but as you increase the temperature, there's going to be a point where this T delta S term gets larger and thus dominates the sign of delta G. Okay, so again, this happens at low temperatures. So let's try to think of a reaction that's both exothermic but entropically unfavorable. One example would be if I convert liquid water into ice. All right, this is a reaction that is entropically unfavorable. I'm creating order. But in order for those liquid water molecules to become solids, they must release heat, right? And of course, the formation of ice is something we know that happens spontaneously at low temperatures, but I'm not really worried about my water spontaneously turning into ice above 0, right? So at high temperatures, this would not be a spontaneous process. Okay. So now, lastly, let's think of what happens if we have an endothermic process. But an endothermic process that is entropically favorable. I want everybody to take a second on your own or with your partner, see if you can determine the sign of delta G at low temperatures versus high temperatures for an endothermic and entropically favorable process. All right, so again, let's think of the extreme low temperature, absolute 0. what would be the sign of delta G? Positive, right? If this term is positive and we're at absolute zero, that means this is zero. So my delta G would be positive, which is again non-spontaneous. But at high temperatures, as I increase my temperature, all of a sudden this term becomes more and more and more important as that T raises. And so there will be a point where now all of a sudden at high temperatures, my entropy term is dominant, which would be negative. The negative T delta S would be negative. And so this would be a spontaneous process at high temperatures. All right, and an example of an endothermic process that's entropically favorable would be if we take liquid water and boil it to form steam or water vapor. Right? My water molecules, they have to absorb thermal energy in order to break out of the liquid phase into the gas phase. So this is an endothermic process. But I'm creating more disorder by turning a liquid into a gas. So this is a reaction that would be non-spontaneous at low temperatures. I'm not worried about water just spontaneously turning into steam at room temperature. But as we raise the temperature, this process occurs spontaneously. Right? So this would be an example of an endothermic and entropically favorable chemical process. All right, so again, if it's exothermic and entropically unfavorable, that's best case scenario from the universe standpoint. It'll let this process happen regardless of the temperature, right? Always spontaneous. And on the flip side, if it's endothermic and entropically unfavorable, the universe is like, no, not going to happen, all right? If there's a mix, if we got a conflict between these two terms, then it's going to be dependent on temperature, okay? So, for example, exothermic and entropically unfavorable. Exothermic's good, entropically unfavorable is bad from the universe's standpoint. It'll let it happen at low temperatures, but there's going to be some high temperature cutoff where it's like, no. No more. All right, and then the opposite for endothermic and entropically favorable. Cool, all right. So one sort of graph that you see a lot with regard to describing chemical reactions or chemical processes is this little hump thing right here. All right, this is the energy of a reaction versus the progress of that reaction, right? So going from reactants to products. So on the left side of this graph, you have the energy of your starting material, your reactants. And on the right-hand side, you have the energy of the products. Okay? We're going to even call this thing free energy, or delta G here. Okay, so there's two important concepts that are kind of intermingled, but we really want to make sure to have them separately in our brain here. And that is the thermodynamics of a process. So what this chapter is all about, right? So spontaneous or non-spontaneous. Yes. Versus the kinetics of a reaction. Okay? And kinetics really correspond to the speed of a reaction rates, right? So kinetics is the speed of a reaction. All right, so it's really easy to kind of think that these two are one and the same, that reactions that are spontaneous happen quickly, reactions that are non-spontaneous don't happen at all, right? They're actually completely separate concepts. There can be reactions that are super favorable from a free energy standpoint. They will happen spontaneously, but they will take 1 billion years to happen spontaneously. They're super duper slow, okay? So this concept of kinetics versus thermodynamics, they're two very different things. This chapter is very much so focused only on the question of thermodynamics, whether or not a reaction happens. We got a whole nother chapter that we'll do later, which will concern the kinetics of a reaction, how quickly it happens. All right, but these are two separate concepts. Just because a reaction happens favorably, just because it's exothermic and entropically favorable, doesn't mean that it happens quickly. Okay, just two very separate concepts. All right, when we're looking at this graph here, the thermodynamics is really only looking at the beginning part over here, the energy of your reactants, and the end point over here, the energy of your products. The bit in the middle, and we'll talk about this when we talk about kinetics, this corresponds to the kinetics of a reaction. All right, but in this chapter, when we're focused on thermodynamics, we're really just looking at the difference between the energy of my products and my reactants. This is the delta G of that reaction, which is all we're really talking about in this particular chapter. Whether or not it happens, right? What's that delta G sign? Okay, so the bottom line is spontaneous does not mean it's fast. Those are two completely separate concepts. All right. One of the things that we're going to see that makes these thermodynamic quantities really useful all of them, delta G, delta H, and delta S, is that these are what are called state functions. All right, and so what the heck do I mean by that? So let's do an analogy here. So let's say that we have this beautiful green field and this pretty mountain. Okay, believe it or not, this is my drawing of a mountain. And we got two hikers that are going to go up this mountain. One of them, the blue guy, is just going to beeline it right up the side. Steepest route possible, just trying to get to the top as quickly as he can, he or she can. Okay? And then we have another hiker, a red hiker, starting at the exact same point. But they are like, screw that, I'm not trying to bust my lungs. I'm going to go ahead and take a nice zigzaggy switchback route up. Okay? They both start at the same place. They both end at the same place. Okay? But in terms of the distance covered, Which hiker traveled a longer distance? Red, right? So red traveled a longer distance than blue. Okay? Distance is what would be called a path function. It very much so depends on the path you take. If you take a shorter route, you get a shorter distance. If you take a longer route, you get a longer distance. Okay? But we could also measure this hike using a different quantity, what's called displacement. All right, and that is just the difference between where you started and where you ended. So n minus start is displacement. Since both of these hikers started in the exact same place and they ended at the exact same place, despite the fact that their distance covered is different because distance is a path function, their displacement of these two hikers is identical, right? So both red and green, blue rather, have the same displacement, right? Because they both started at the same point and ended at the same point. Again, distance is what we call a path function. Displacement is what we call a state function. Doesn't matter how you got there. All that matters is where you start and where you end. All right. So, extending this to chemistry here. Again, these thermodynamic quantities are state quantities. Right? So what does that matter? Delta G, delta H, and delta S are the same for a reaction that occurs in one step or if we do the same reaction but it breaks up into multiple steps. All right, so just to sort of illustrate this, let's say that we take nitrogen gas and mix it with oxygen gas to form tetranitrogen dioxide. And then we measure the delta G of this reaction. I don't know, it's equal to something, some variable, x. If instead we took these same two reactants, but then first converted them into dinitrogen monoxide, and then in a second step converted that dinitrogen monoxide into that same product. I guess I gotta do this. The delta G of this reaction and this reaction combined would be that same delta G of the first, right? So if we did this reaction in one step, or we broke it up into multiple steps where the net reaction was the same, we'd have the same free energy because delta G is a state function. All right, this turns out to be a super duper useful property of these thermodynamic quantities. Okay, so an important part of this chapter is going to be our constants page for this chapter, where, and it's not just a page, constants book for this chapter. All right, whoops, what am I doing? Okay, where we have these compounds listed, and then for each compound there's a delta H, a delta G, and an S tabulated here. All right, and we can look up a bunch of different compounds here. Actually not down there, but yes. All right, each one of these, let's take a look at this here. We're going to use this in a second, so we'll just grab this. Gives us the, again, it was delta H, delta G, and S. They had these little knots on there, which I'll explain in a second. But so let's say that I take one of these lines. This gives me the delta G, the delta H, and the entropy of what's called a formation reaction, where we take each element in its standard state. So hydrogen gas plus oxygen gas gives me liquid water. That would be the delta G, delta H, and entropy of that reaction in blue there. Okay, if I looked at this other entry here, this would be the formation reaction for not liquid water, but gaseous water. So same sort of idea, same reactants, always elements in their standard state. All right, but the bottom line is I can use these values to figure out the delta G, delta H, and entropy for any reaction. Okay, so let's say I wanted to figure out what the delta G, delta H, and entropy were for when liquid water is converted to gaseous water, right? A vaporization reaction. Right? If I combine these two equations, so I'm going to take this one with my water that's a gas on the product side. I'm going to take this one with the water that's a liquid, but I'm going to flip it around. All right, so you're over here, and you're over here. When I combine these two reactions, what's going to cancel out? The hydrogens are going to cancel out. The oxygens are going to cancel out. And so my net reaction will just be that one that I wanted in the first place. All right, so the bottom line is we can use these tabulated values here They correspond to these specific formation reactions, but because we can then use them and mix them, match them, we can figure out the delta G, delta H, and entropy for any reaction. All right, so that's kind of the why of it. Let me just give you the simple explanation of how we go about doing this. All right, so again, we're going to use our same values here. Again, I want to do the reaction of liquid water being converted to gaseous water. Okay, if I want to calculate the delta G of this reaction, I'm going to be able to do it using the delta G of our tabulated values here. Okay? When we're building equilibrium constants, we always chant to ourselves, what over what? Products over reactants, all right? When it comes to these thermodynamic quantities, we're going to have something similar, except for it's going to be products minus reactants. So the delta G of my products minus the delta G of my reactants will give me my delta G of my overall reaction here. All right, so let's say that I'm going to do it for this reaction here. I'm going to take my products, which is the gaseous water. All right, so be careful. We got a bunch of compounds listed. Make sure you're also matching the states as well. All right, so my product is the gaseous water. So I'm going to take that negative 228.6. The units here are kilojoules. And I'm going to subtract my reactant side, negative 237.1 kilojoules. And I see that the delta G of this reaction is 8.5 kilojoules. All right. Going back to our table here, one thing I want to point out. Our delta G's, delta H's, entropies, they all have this little knot on there, this little circle up at the top. Right? This means that these are the thermodynamic values for these reactions at what's called standard state. And we'll talk a little bit more about what standard state is. The first sort of condition that we're going to have is standard state is specifically 25 degrees Celsius. So these are these enthalpy, entropy, free energy values that you would get for conducting these reactions at 25 degrees Celsius, right? A specific temperature. So if we go back here to our math that we just did, except I lost it. There we go. According to my delta G here, is this reaction spontaneous or non-spontaneous? So this is non-spontaneous. But if we're being good, we would note that it's not just that this is delta G naught, which again corresponds to a specific temperature. So this reaction we've demonstrated is non-spontaneous at 25 degrees Celsius. All right, and based on what we know about converting liquid water to steam, does that check out? right? Is that something that occurs just randomly at room temperature? No, so that's not going to be a spontaneous process at room temperature at 25 degrees Celsius. That process is indeed non-spontaneous, all right? What we will show next time is that if we crank up the temperature, then all of a sudden that delta G becomes negative, all right? But for now, what we really want to note is that we can use our thermodynamic table to figure out these thermodynamic quantities by taking products minus reactants. All right, so everybody take a second real quick in our last few minutes and tell me what the enthalpy is of this reaction here. All right, your delta H naught of this reaction. And it's the same idea. If I'm going to get my delta H, it's going to be the delta H of the products minus the reactants. So again, building equilibrium constants, we said products over reactants. In this chapter, we're going to say products minus reactants. That's always how we get our thermodynamic values. So again, my product is the gaseous water. I'm going to take that negative 241.8. I'm going to subtract the delta H of my reactant, the negative 285.8. And I would get that the delta H of this reaction is 44 kilojoules. Let me just bring our chemical equation down here so we can sort of see it next to each other. So according to our calculations here, is this reaction endothermic or exothermic? Endothermic, right? A positive delta H is an endothermic reaction. And based on what we know about phase changes, does that check out? All right, so it's really important that you guys understand that if anything's being converted from a liquid to a gas, it has to absorb thermal energy to do it, right? Those liquid water molecules have to absorb thermal energy to break away from the pack. So all of these vaporization processes will be endothermic. So that checks out based on what we would expect just by looking at our chemical equation. If we calculated delta S, what would we expect it to be for this reaction? Positive or negative? Positive, because we're getting a gas. And so indeed, you can use these values and convince yourself of that, all right? So we'll use this table more next time to learn a little bit more about reactions.